Hey there, science fans! Ever wondered how computers think? Well, they don't actually think like you and me. They rely on a powerful little chip called the Central Processing Unit, or CPU for short. Think of it as the brain of the computer. Inside the CPU, millions, even billions of tiny switches called transistors are hard at work. These transistors are like tiny light switches that can be turned on or off. When electricity flows through, the switch is on, representing a 1. When it's off, it's a 0. This simple system of ones and zeros forms the foundation of how computers process information. Pretty neat, huh? Now you might be wondering how just two numbers, 1 and 0, can represent all the complex information computers handle. It's like a secret code. This code is called the binary system. Imagine a light switch. It can be either on or off, just like our ones and zeros. By combining multiple switches, we can create different patterns. Two switches give us 4 possibilities: on-on, on-off, off-on, off-off. Each of these combinations represents a unique binary number. We call a group of 8 of these ones and zeros a byte. Bytes are the building blocks of all the data stored and processed by computers. Writing long strings of ones and zeros can get pretty tedious, wouldn't you say? That's where hexadecimal comes in handy. It's like a shorthand for binary. Instead of using just 0 and 1, hexadecimal uses 16 different digits, 0 through 9 and A through F. Each hexadecimal digit represents a group of 4 binary digits. This makes it much easier for us humans to read and write large binary numbers. Don't worry too much about the specifics. Just know that hexadecimal is a useful tool for programmers and computer scientists. It's like using abbreviations instead of writing out full words. Now, how do those transistors actually process information? They do it with the help of logic gates. Logic gates are like tiny electronic circuits that perform simple logical operations. There are different types of logic gates like AND, OR, and NOT gates. Each gate takes one or more binary inputs, ones and zeros, and produces a single binary output based on its specific logic. For example, an AND gate only outputs a 1 if both of its inputs are 1. By combining these simple logic gates in different ways, we can build complex circuits that perform all sorts of calculations and operations. Section 5. From letters to emojis, how computers understand characters. In this section, we will explore the fascinating world of character encoding and how computers make sense of the diverse range of characters we use every day. We've talked about ones and zeros, the fundamental building blocks of digital information. But what about letters, numbers, and even emojis? How do these symbols get translated into a language that computers can understand and process? How do computers understand those? This is a question that delves into the core of computer science and digital communication. That's where character encoding comes in. Character encoding is a crucial system that bridges the gap between human-readable text and machine-readable binary code. Character encoding is a system that assigns a unique binary code to each character. This allows computers to store and manipulate text efficiently. One of the most common encoding systems is ASCII, which stands for American Standard Code for Information Interchange. ASCII uses 7 bits. A bit is a single 1 or 0 to represent 128 different characters. This includes a wide range of symbols that are essential for basic text communication. A bit is a single 1 or 0, the smallest unit of data in computing. ASCII can represent 128 different characters, which include letters, numbers, and various symbols, including uppercase and lowercase letters, which are fundamental for writing and communication. Numbers, punctuation marks, which are essential for structuring sentences and conveying meaning, and some special control characters, which help in text formatting and control. For more diverse characters like emojis, which add emotion and context to digital communication, we use other encoding systems like Unicode, which is a more comprehensive system. Unicode can represent over 143,000 different characters, covering almost all the writing systems in the world, as well as a vast array of symbols and emojis. Section 6. The conductor of the orchestra The role of operating systems. Imagine a giant orchestra with all its different instruments. To make beautiful music, you need a conductor to coordinate everything. That's what an operating system does for a computer. An operating system, or OS for short, is a software program that acts as the intermediary between the user and the hardware. It manages all the computer's resources, like the CPU, memory, storage, and peripherals. Some popular operating systems you might know are Windows, macOS, and Linux. The OS provides a user interface for us to interact with the computer, runs applications, manages files, and ensures everything runs smoothly. It's the unsung hero of the computer world. Section 7. The CPU's dance: fetch, decode, execute, store. We know the CPU is the brain, but how does it actually process instructions? It follows a cycle called the fetch, decode, execute, store cycle. It's like a dance the CPU performs millions of times per second. 1. Fetch. The CPU fetches the next instruction from memory. 2. Decode. It then decodes the instruction, figuring out what it needs to do. 3. Execute. The CPU performs the operation specified by the instruction. 4. Store. Finally, it stores the result of the operation back in memory. This cycle repeats continuously, allowing the CPU to execute programs and perform tasks. It's a well-choreographed dance that keeps our computers humming. Section 8. Talking to computers, the world of programming languages. If we want to tell a computer what to do, we need to speak its language, but, computers don't understand English or Spanish, they understand programming languages. Programming languages are formal languages designed to communicate instructions to a computer. There are many different programming languages, each with its own syntax and rules. Some popular programming languages are Python, Java, and C++. Programmers write code using these languages to create software, websites, games, and much more. It's like writing a recipe for the computer to follow. Section 9. Storing information, variables, and data types. In this section, we will explore how computers manage and organize data using variables and different data types. Just like we use boxes to store things, computers use variables to store data. Imagine each variable as a labeled box where you can keep specific items. A variable is like a container that holds a value, such as a number, a word, or a sentence. This allows the computer to access and manipulate the data efficiently. Each variable has a name and a data type. The name is a unique identifier, while the data type defines the kind of data the variable can store. The data type tells the computer what kind of information the variable can hold. This is crucial for ensuring that the data is processed correctly. Some common data types are integers, which are whole numbers like 10, 25, or -5. These are used for counting and calculations that don't require fractions. Floats, which are numbers with decimal points like 3.14 or -2.5. Floats are essential for precision in scientific calculations and measurements. Strings, which are text values like hello or computer science. Strings are used for storing and manipulating text. And booleans, which are true or false values. Booleans are fundamental in decision-making processes within the code. By using variables and data types, programmers can organize and manipulate data efficiently. This organization is key to writing clear, maintainable, and efficient code. Section 10. Memory management, keeping things tidy. Computers have a limited amount of memory, so they need to manage it carefully. This is crucial for ensuring that all programs run smoothly and efficiently without any interruptions. That's where memory management comes in. It plays a vital role in the overall performance of a computer system. Memory management is the process of allocating, using, and freeing up memory space. It involves a series of steps to ensure that memory is used optimally. When a program needs to store data, it requests memory from the operating system. This request is handled by the memory manager, which allocates the necessary space. When the program is done with the data, it releases the memory back to the system. This is known as deallocation, and it helps in making the memory available for other programs. This process ensures that memory is used efficiently and prevents programs from running out of space. Efficient memory management is key to maintaining system stability and performance. One important aspect of memory management is garbage collection. This is an automated process that helps in cleaning up unused memory. Garbage collection is like taking out the trash. Just as you remove waste to keep your environment clean, garbage collection removes unnecessary data to keep the system running smoothly. It's the process of identifying and removing data that is no longer needed by the program, freeing up memory for other tasks. This not only optimizes memory usage but also enhances the overall efficiency of the computer system. Section 11. Arrays, organizing data. Like a pro. Imagine you have a collection of items like a grocery list or a deck of cards. How would you organize them? You could use an array. An array is a data structure that stores a collection of elements of the same data type. It's like a list where each item has a specific position or index. Arrays are incredibly useful for organizing and processing large amounts of data. For example, if you were writing a program to store student grades, you could use an array to hold all the grades for a particular class. Arrays make it easy to access, sort, and manipulate data in efficient ways. And there you have it.